burn like a pro.
All right, chemistry exam on the horizon? You've come to the right place. We're going to do a super focused cram session on a topic that is almost guaranteed to be on there, fuels and crude oil. My goal? To get you totally prepped to crush this thing. Yep, this is your personal last-minute study guide. We're going to hit all the big ideas, the key definitions, and the processes you absolutely, positively have to know. So grab your notes, get focused, and let's dive right in. Okay, here's our game plan. First, we'll cover the basics of fuels. Then, we'll time travel back millions of years to see where crude oil even comes from. After that, we'll get into the really cool chemistry of how it's refined, and we'll wrap it all up with a quick hitter review to make sure it all sticks. All right, section 1. Let's start at the very beginning. We gotta nail down the basics. So, what is a fuel anyway? Okay, definition time. A fuel is basically anything that gives off a ton of heat when you burn it with oxygen. And that burning process? It has a very specific name you have to know for your exam. It's called combustion. Super important. It's an exothermic reaction. Exo means out, thermic means heat. It releases energy. Simple as that. So, who are the main players here? We're talking about the big three fossil fuels: natural gas, coal, and petroleum. Now, the two things you got to remember about them are, 1, they're all organic compounds, which just means they're built around carbon. And 2, and this is the big one, they are non-renewable. When they're gone, they are gone. For good. Okay, so where does this stuff, this black gold, actually come from? I mean, it doesn't just appear, right? Turns out it's the end result of an incredible story that took millions of years to unfold. Picture this. Millions and millions of years ago, the oceans were full of tiny plants and animals. When they died, they just sank to the bottom. Over time, they got buried deeper and deeper under layers of mud and sand. All that pressure from the rocks on top, plus the heat from the Earth's core, basically acted like a giant pressure cooker. It slowly cooked those remains and turned them into crude oil and natural gas. And this is how we get our hands on it today. After all that time, we build these massive oil rigs to drill way down through all those layers of rock to get to the oil and gas that's been trapped down there. A little fun fact for your exam: see how the gas is usually found in a pocket right above the oil? That's a super common formation. Okay, now we're getting to the heart of it. This is the part that shows up on exams all the time. How do we take that thick black goo and turn it into something useful, like gasoline? The magic word here is fractional distillation. You're going to want to write this one down. Fractional distillation is simply the process we use to separate crude oil, which is just a big jumble of different hydrocarbons, into useful batches called fractions. And the whole trick relies on one simple fact: different sized hydrocarbons boil at different temperatures. So this is what it looks like in action. This is the fractionating column. If you remember one thing about this diagram, make it this: it is blazing hot at the bottom and gets cooler and cooler as you go to the top. This temperature difference, this gradient, is literally the secret to the entire process. Let's imagine we're a hydrocarbon molecule for a second. First, we get heated up into a gas and shot into the hot bottom of this tower. As we rise up, we start to cool down. Now, if we're a small short-chain molecule, we have a low boiling point. That means we can travel way up to the cooler parts of the column before we finally turn back into a liquid. But if we're a big, long-chain molecule, we have a high boiling point. We'll turn back into a liquid much sooner, way down in the hotter section of the column. Okay, this table, this is pure gold for your exam. It connects everything. As you go down the column, the molecules get bigger, right? Longer chains. Because they're bigger, the forces holding them together, the intermolecular forces, are stronger. And because those forces are stronger, you need more energy to break them apart, so the boiling point goes up. These bigger molecules are also less flammable, more viscous, that's a fancy word for thick and gloopy, and less volatile, meaning they don't evaporate easily. It all comes back to molecule size and those intermolecular forces. Understand that, and you've got this. So fractional distillation is pretty brilliant, right? But it's not perfect. It actually creates a big problem for the industry. So let's talk about what that problem is, and more importantly, how chemists figured out a way to solve it. It really just boils down to supply and demand. Think about it. What do we want most? Smaller hydrocarbons like gasoline for our cars. But what does fractional distillation give us? A ton of large, heavy, not so useful hydrocarbons. So we're left with way too much of the stuff we don't want and not enough of the stuff we desperately need. And the solution? It's a process called cracking. And yeah, it's pretty much exactly what it sounds like. We take those big, long, clumsy hydrocarbon molecules that nobody wants, and we literally crack them. We use heat and catalyst to break them apart into these smaller, more useful, more valuable ones that everyone is after. Now remember, we said crude oil is non-renewable. That means we can't just use it forever. So conservation is a huge deal. The exam might ask for some strategies. 3 big ones are: 1, just use less, right? Take the bus. 2, find other ways to make energy, like solar or nuclear. And 3, make the things that use fuel, like our cars and power stations, way more efficient. So, all this talk of running out of oil leads to a big question. What's next? One of the big ideas on the table is biofuels. But are they really the green miracle we're hoping for? Let's weigh the pros and cons. So what is a biofuel? Simply put, it's fuel made from renewable stuff. You know, living things, like plants. The classic example you'll probably see is bioethanol. It's basically just alcohol that's made by fermenting the sugar in plants like sugarcane. But here's where it gets complicated. It's not a magic bullet. The huge advantage, of course, is that they're renewable. We can just grow more corn. But the downside? Well, you need a massive amount of land to grow all those crops, land that could be used for food. And here's the real kicker. You often have to burn fossil fuels to clear the land, make fertilizer, and transport the crops, which kind of defeats the purpose, doesn't it? Okay, deep breath. We're on the home stretch now. This is the final cram session. Let's do a super fast, rapid-fire review to make sure you've got all the key points locked in your brain. Ready? Let's go. What's combustion? An exothermic reaction when fuel burns in oxygen. What's non-renewable? An energy source you can't replace quickly. What's a hydrocarbon? A compound with only carbon and hydrogen. Got 'em? Awesome. Okay, listen up. This is a super common exam pitfall. You have to know how to balance combustion equations. They love asking this. Let's take methane, the stuff in natural gas. It's CH4 plus 2O2 gives you 1 CO2 and 2 H2O. Just burn that equation into your memory, trust me. All right, here's one last brain teaser for you. Pure natural gas is completely odorless. So, how can you smell a gas leak? Think about it. The answer is, they add something to it. Gas companies mix in a harmless but really stinky chemical so that we can detect leaks immediately. That gas smell is all for safety. Pretty cool, huh? Okay, you've got this. Go ace that exam.